on the wave of optics. Each of the concepts covers 2 chapters and 2 tutorials. Okay, so our first week is designed for geometric optics. Okay, so actually, what I'm going to talk about is reflection and refraction of light. I think some of you also are already quite familiar with this concept. But if you already attend, so how many of you have already attended the summary lecture? May I ask? Okay, so about half. So very good. Okay, so if you also attend the lunch, you can see maybe there are about 3-hour lunch. Many concepts have been introduced there. But if you look at my summary here, I would say here, all the concepts about the first chapter, okay, can only be summarized as 1 concept, 2 formula or 2 laws, and 2 phenomena. 1 to 2. Okay, 1 to 2. 1 concept, 2 laws, and 2 phenomena. So the first concept we introduce is what we call the plane of incidence. So what the plane of incidence is so introduced like this. What we know is light incident upon the surface of the material. Of course, it will be reflected, right? Like laser beam incident on a mirror, it will be reflected. Okay. Then, in order to understand how the light will be reflected, we first need to define a new concept, that is the plane of incidence. The plane of incidence is the plane formed by the incident light ray, the reflected light ray, as well as the surface normal. Again, plane of incidence is formed by the incident light ray, reflected light ray, and the surface normal. This is what we call the plane of incidence. This gray plane here is the plane of incidence. This guy here is our mirror, reflecting mirror. Clearly, the plane of incidence is not this reflecting surface. Is a plane that is perpendicular, like for example, light is reflected from this desk. This desk surface is not the plane of incidence. A plane that is perpendicular to it is my plane of incidence. The plane of incidence is where the incident light ray and the reflected light ray lines, okay, is always perpendicular to the reflecting surface, okay? So when we talk about reflection or refraction, we are normally looking at the plane of incidence, okay? This is a new concept. Then I will come to 2 laws. With the plane of incidence, we will be able to discuss how the light is reflected and refracted. So first, the law of reflection. So this line here is now my reflecting plane. We are looking at the whole plane here is my plane of incidence. So this is my reflecting mirror, incident light ray, and reflecting light ray. Then in the plane of incidence, we can define 2 angles. The first angle is what we refer to as the incident angle. Okay, the incident angle is the angle formed by the incident light ray and the surface normal. So similarly, we can define the reflected angle. Okay, the angle of refraction formed by the reflected light ray and the surface normal. Then the law of reflection always tells us that incident angle theta I is always equal to the reflected angle theta R. Okay, these 2 angles are always equal to each other. Always equal to each other. So that if the angle theta I is larger, whether obliquely incident upon the surface, and theta R should also be larger.
Hello, prof. Hello, prof. Okay, yes.
Yes, theta R should also be larger. Okay, so I think there is some other. Theta R should also be larger.
Prof.
Yeah, hello?
Yeah, just print prof.
Yes.
Okay, it's back. The screen was frozen, Prof.
Oh, screen frozen now, sorry. How about now? Is the screen moving?
Yes, Prof.
Now it's moving, right?
Yes,
Okay,
Prof.
so maybe I will start from the law of refraction. Okay, I start from the law of refraction. So because the previous plane of incidence is very easy now. Okay, as I said, just formed by the incident light reflected light ray on the surface normal. And then for the law of refraction is the incident angle always equal to the reflected angle. Incident angle always equal to the reflected angle. If the incident light ray is incident very obliquely with a very large theta I, so that my theta R should also be very large. Okay? Any question about the law of reflection? Okay, so if you don't, then I will have a question for you. I hope every one of you should try to look at this. This shows a general case where my light incident upon the surface, obliquely incident upon the surface. If my incident light is along the surface normal, what will be the direction of the reflecting light? Again, if my light is now incident along the surface normal, what will be the direction of the reflected light? Yes, still online? Any suggestion? You can just unmute yourself and speak. How about student in the classroom? If my light is going along the surface normal, what will be the direction of the reflected light? Any idea? Yes, very good. Still along the surface normal, but straight up. Very good. Because in this case, if my light is along the surface normal, according to the definition of the incident angle, okay, it's the angle between the incident light ray and the surface normal, so that my theta I is 0. Theta I is 0, my theta R should also be 0, so that it's still along the surface normal, but straight up. Just changing the direction. Very good. So then the law of refraction. Now let's look at the law of refraction. So if we have light incident upon a material, for example, like the glass or water, some portion of light, small portion of light will be reflected, but a large amount of light will go into the material. But it will not propagate along the original direction. It will change direction. It will propagate along another direction, theta 2 here, okay? This is what we call the formula of refraction. When light passes through the interface of two materials, it will change in direction. Such phenomenon is called refraction. Then, of course, we want to know how the light will be refracted. We will define two angles. The incident angle is still defined as the angle between the incident light ray and the surface normal. Refracted light ray, angle of refraction is defined as the angle between the surface normal and the refracted light ray, okay? And the refracted light ray, this is theta 2 here. Then, yes?
The only two people say the screen frozen.
Sorry?
The two people say the screen frozen.
The screen still frozen?
Yeah. Still showing the previous slides.
Oh, it's still showing your previous slides.
Yeah.
Okay. What happened? Let me reshare. Frozen again. Okay, so thank you. So now I share on the first screen. So if I move, is it frozen or move? Could you help check? Yes, is it moving? Is the slides moving? Yeah, this is not time, right? Okay, good. Okay, so now let's look at the law of refraction. Okay, so the law of refraction tells us that, okay, the sine function of the incident angle divided by the sine function of the refracted angle always equal to a constant. This is the law of refraction. Or mathematically, we call n1 times sine theta 1 always equal to n2 times sine theta 2, with theta 1 and theta 2 as the incident angle and the refracted angle respectively. n1 and n2 is what we call the refractive index. Okay, refractive index. So in the summary lecture or in the lunch, so the lecture here talk a lot about what the refractive index is. Then what I can say is the refractive index is a fixed constant for a material. Okay, is the ratio between the free space light velocity and the speed of light in that medium. Okay, the speed of light in that medium. The ratio between C vacuum light velocity vacuum divided by the light velocity in that material. That is what we call the refractive index. Once the refractive index is known, and then we will be able to use such index to calculate how light will be refracted. It's always n1 times sine theta 1 equal to n2 times sine theta 2. Okay, n1 times sine theta 1 equal to n2 times sine theta 2. Okay, so it's always like this. So you can see in the law of refraction, we have 4 parameters: n1, sine theta 1, theta 1, n2, theta 2. So knowing only 3 parameters out of this 4, you will be able to use the law of refraction to get the fourth one. So this is how the law of refraction will be normally tested. Okay. Yes. This is how the law of refraction will be tested. Then, any question? I already talked about the 2 laws. So if law, then let's talk about what the 2 phenomena you have to understand. Okay. So both 2 phenomena are related with the refraction. Okay. So first, you have to understand the refractive index. The refractive index n is not a constant. It's actually wavelength dependent. You know, light have frequency, have wavelengths. So for example, our sunlight have different color. Different color corresponds to different wavelengths. Okay, right? Different wavelengths corresponds to different color. For example, we have the sunlight. It constitutes the color from yellow, red, yellow, green, blue, right? And each color have different wavelengths. The red light happens at longer wavelengths, has the longest wavelengths, while blue light or violet light has the shortest wavelengths, And then the reflective index of the material is not a constant across the wavelengths, but it has to be changed. Okay, smaller wavelengths actually reflective index will normally be. So for fixed material, smaller wavelengths will have larger reflective index. Longer wavelengths will have small reflective index. But this is not a constant. So take the glass as an example. Okay, we have your attention. Take the glass as an example. At the red light, longest wavelength, it has a reflective index about 1.51. Why it shoot up to 1.53 at 400 nanometer blue light, 400 nanometer blue light. So that the reflective index is not a constant. Even for glass, is not a constant. Different color will see different reflective index. Red light, longest wavelength, we have the smallest reflective index. Blue light, shortest wavelength, we will see the largest reflective index. Okay? So this is what we call the chromatic effect, N depends on the wavelength. Then the second phenomenon, so is the last concept we have to learn is total internal reflection. Okay. So you know, normally when light incident upon the interface, okay, we will have both reflection and refraction. Okay, reflection and refraction. Okay. Okay. So, let me stop. So for students attending online, so if you see my frozen of my slides, you just unmute yourself and let me know. Because I am sharing the screen in the full screen mode. You test in the chat room, I cannot say, instantaneously. Okay, so you can just unmute yourself and let me know any problem you have. Do not type in the chat room because I cannot say instantaneously. I think this is the problem of the MS Team. Okay, now let me continue. So normally when light incident at the interface, it will have both reflection and reflection. But sometimes when light incident upon the interface, it will only have reflection without any refraction. That is what we call total internal reflection. Total internal reflection. So there are two criteria for the total internal reflection to happen. Two criteria for the total internal reflection to happen. So first, my light source must be put in the high index material. My light source must incident from the high index material. So for example, if we have this glass on the air interface, if I incident from air, the low index material, I will not have the total internal reflection. Only when I put my light source in the glass whose reflection index is larger, I can get the total internal reflection. Only the light source placed in the high index material, that is not enough. We have to satisfy a second criterion, is the incident angle must be larger than a certain critical value. So for example, if I have my incident angle, very close to the surface normal for this two beam, even I am in the glass, I can still get reflection. Refraction. I still have reflection. You can say both reflection and the reflections happens if my theta is not large enough. But then if my light is larger than this critical value, for example, theta c, then I no longer have reflection. For example, for this yellow ray, and also this theta 1 is even larger than theta c. Is even larger than theta c here. I don't have any refraction, only live with the reflection. That is what we call the total internal reflection. Okay. Sorry?
The beam froze again.
Frozen again, yeah. Really?
Prof, we are still on law of refraction. I think maybe it's because of the presenter mode.
So maybe I share the screen. How about now?
Yeah, we
Is
see.
it moving?
Okay, yeah, it's moving now.
It's moving now, okay?
Yes.
Good.
Yes.
Okay, thank you. So you let me know also if it's frozen, okay? So yes, the total internal reflection. So let me repeat. The two criteria for the total internal reflection to happen. The two criteria for the total internal reflection to happen is first, my light source has to be placed in the high index material. Light source has to be placed in the high index material. Then my incident angle theta 1 must be larger than this critical value. So if it's smaller than this critical value theta c, we have refraction. Only when my theta 1 incident angle larger than this critical value, then I don't have any refraction. Okay, and this critical value is calculated as theta c equal to arc sine n2 divided by n1, or you can say the critical value is where the refracted angle is parallel to the interface, which means my refracted angle is 90 degrees. So theta c is calculated by setting theta 2 equal to 90. Okay, theta equal to 90. So that my theta c equal to arc sine n2 divided by n1. Only when my incident angle theta 1 is larger than this critical value, I get a total internal reflection. Okay, total internal reflection. So two criteria. One, light source is a high index material. Second, I have to be larger than the critical angle. Okay, any question? Any question? Okay, so now I move to the tutorial question. So student online, let me know again whether my slide is frozen.
It's okay, Prof.
Okay, good. Thank you. Okay, so let us say we have 5 tutorial questions. Maybe I will continue cover 1 or 2 past examination papers. Okay, so first one, we have a laser beam incident at an angle 30 degrees from the surface normal onto a solution of corn syrup. If the beam is refracted to 19.24 degrees from the vertical, which means incident angle is 30, refracted angle is 19.24. So what's the index of the corn syrup solution? Okay, corn syrup solution. I think this question is very easy. Tells you about direct application of the law of refraction. Okay, as I said, for the first chapter, we only have 2 formulas. Okay, 2 formulas: law of refraction and the law of refraction. And normally, what will be tested is the 2 phenomena: total internal refraction or the chromatic effect. So the first one is very easy. Okay, just directly test you to apply the Snell's law. So the law of refraction. So, you know, in the law of refraction, we have n1 times sin theta 1 equal to n2 times sin theta 2. As I already mentioned, 4 parameters in this equation. No only 3 out of this 4 parameters, we will be able to use the Snell's law of refraction to calculate the 4th one. For this question, light incident from air clearly reflecting index equal to 1. Incident angle and the reflected angle are both given. So which means my n1, theta 1, theta 2 are given. What left unknown is only theta 2. So that you substitute all the 30 degree, 90.4 degree, as well as n1 equal to 1 into the Snell's law. You can directly show n2 equal to 1.52. Okay, n2 equal to 1.52. Okay. Any question? Good. Now let's look at question two. Okay, we have light with a wavelength of 700 nanometer incident onto the surface of a cool .46. The incident angle is 75 at the first interface. Okay, at the first interface, the apex angle of the prism. So apex angle is this guy. The apex angle of the prism is 60 degrees. Okay, 6 degrees. The question has 4 parts. First, we have to calculate the angle of refraction at the first interface. Then the angle of incidence at the second interface. C, the angle of refraction at the second interface. And finally, the angle between the incident and the emerging rays. Incident and emerging rays. These are the 4 parts of the question. Let's look at these 4 parts one by one. Okay. First, what is the angle of refraction at the first interface? Okay, I highlighted by red line here. What is theta 2? So this question tells us to directly apply Snell's law. Okay, directly apply Snell's law. Okay, because theta 1 is given, refractive index of the prism is given 1.46. Incident from air n1 equal to 1. So which means here n1, n2, theta 1 is given. So we substitute the value for these 3 parameters into Snell's law. You can directly calculate theta 2 equal to 41.4 degrees. 41.4 degrees. So now question 2. Question 2 asks us to calculate theta 3. The incident angle at the second interface. Okay, now I highlight the second interface here. I need to calculate theta 3. Theta 3. Okay. So in order to get 3, there are no only law of physics. Physics law we can apply, but we can calculate theta 3 mathematically. Okay. So bear in mind theta 2 is given. So looks like there is not any relationship between theta 2 and theta 3, right? But bear in mind, the dashed line here are the surface normal. Dashed line here are the surface normal. Now, if we define another two angle, we will be able to find the relationship between theta 2 and theta 3. Okay, theta 2 and theta 3. Because this is the surface normal, which means my alpha plus theta 2 equal to how much? Any idea? Alpha plus theta 2 equal to how much? Very good, 90. Similarly, my beta plus theta 3 should also equal to 90, right? Now, bear in mind, theta 2 is what we have already calculated, okay, in previous slides, 41.4 degree. Now, due to the surface normal condition, okay, we get two relationship between theta 3 beta, theta 2 and alpha. So there are three unknown parameters, alpha, beta, and theta 3, okay, alpha, beta, and theta 3. We already get two. We should look for a third equations so that we will be able to determine, all alpha, beta, and theta, all three parameters. Now, can you tell me what are the third equation we should look at? Or are there any relationship between alpha and beta? Are there any relationships between alpha and beta? Any idea? Student and team, am I there? Very good. What we should look at is the total internal angle of a triangle. I highlighted by the gray area here, should equal to 180, right? The total internal angle of a triangle should be 180. So we should look at this triangle. So the third relationship we should write at is alpha plus beta plus this 60 degree equal to 180, equal to 180. Now there are three equations, three parameters we can solve for all three unknown parameters, alpha, beta, and theta 3. So the way to solve that is we look at the second and third equations plus the left-hand side and the right-hand side together. We have this alpha plus beta plus theta 2 plus theta 3. Okay, so all the left-hand side plus together, we get this guy. 90 plus 90 equal to 180. Then this guy equal to 180, which is alpha plus beta plus 60. Right? So this one and this one should equal to each other. We neglect alpha plus beta. We can directly show my theta 2 and theta 3 equal to 60 degree. Theta 2 plus theta 3 equal to 60 degree. Okay? Now here comes an important conclusion, so which is quite often tested in the final examination, okay? Because final examination, if the law of refraction is tested, normally we will test in prism. As long as the law of refraction is tested, normally it's in prism. So for prism, there is one important relation between theta 2 and theta 3. So what I call the two angle inside the prism. The two angles inside the prism, the summation of them is always equal to the apex angle. Okay, theta 2 plus theta 3 always equal to the apex angle. If the apex angle here is 60, is equal to 60 degree. If it's 30, if this angle is equal to 30, then theta 2 plus theta 3 equal to 30. If it's 90, okay, theta 2 plus theta 3 then equal to 90. But this relationship, I suggest every of you try to remember it because it will try to help you speed up your solution to the question. Or you can remember the solution, how to prove theta 2 and theta 3 equal to 90 or equal to this apex angle. But if you think, okay, this procedure is very complex, you can directly remember the calculation and the conclusion I give to you. Theta 2 plus theta 3, the two angles within the prism always equal to the apex angle. Summation of the two angles inside the prism always equal to the apex angle. Okay, this is an important conclusion. Although it will not be given in your formula sheets, the law of refraction, this formula will be given in your formula sheets. But this guy, as I said, theta 2 plus theta 3 equal to the apex angle, that will not be given in your formula sheet. But it's an important conclusion which you can remember and directly use it, okay? And directly use it in your solution. Okay, so I think this is a very useful conclusion. Every one of you try to remember it. Okay, so inside any prism, the two angle within inside the prism, their summation always equal to the apex angle. Okay, so with such condition in mind, you can just say, okay, my apex angle minus theta 2, I can get a theta 3, so which is 80.6 degrees. 80.6 degrees. Now theta 3 is given. The third part wants us to calculate theta 4. Okay, part C wants us to calculate theta 4. So that we directly apply Snell's law as this interface. Now this has a reflective index N2. Okay, so now my N2 times sine theta 3 should equal to N1, which is the air, reflective index of air times sine theta 4. So that substitute all N1, N2, and theta 3 we get, and then you can directly calculate it. Theta 4 equal to 27.8 degrees. 27.8 degrees. So now the last question wants us to calculate the angle between the incident light ray and the final emerging ray. So the angle between this, thick solid arrows. So this is very interesting because these two solid arrows, they do not intersect. In order to calculate their angle, we have to extend the two rays, let them intersect. So if in your final examination, the question asks you to calculate the angle between, for example, any two rays, but these two rays do not intersect directly, you have to extend these two rays, let them intersect. Okay, so if these two rays intersect in this way, the angle between them is defined as gamma. Okay. In order to calculate what gamma it is, we have to look at this triangle. Okay, this small triangle here. Okay, this guy and this guy is their extension. Okay, we have to look at this small triangle here. For this small triangle, gamma is the external angle of this apex. Okay, is the external angle of the apex. So for any triangle, the external angle is equal to the summation of the other two internal angles. Because the external angle plus the internal angle always equal to 180 degrees. Okay, so this is why this guy always equal to the summation of this one and this one. So in order to calculate the gamma, we need to calculate this angle and this angle respectively. Now let's first look at the bottom left angle. So this one. The bottom left angle, you can say, so it's not very obvious. But if you bear in mind, the dashed line is surface normal. Surface normal and this blue line is theta 1. Now, if we look at the right-hand side, this angle, dashed line and the blue line on the right-hand side here, this should also be theta 1. Then my theta 1 minus theta 2 should be the bottom left angle for this small triangle. So which means this guy here should be theta 1 plus minus theta 2. Now, using the sum procedure, can you tell me what should be the angle for the bottom right angle? What's the value for the bottom right angle? Still, looking at the angle between the dashed line and the solid blue line, what should be this value of this angle? Any idea? Any idea?
Theta 4 minus theta 3.
Yes, very good. Thank you. That is the right answer. So now we look at the angle between the dashed line and the solid line. You can say this angle between the blue and the dashed line here should be theta 4. Then theta 4 minus theta 3 is the bottom right angle. So this is theta 4 minus theta 3. Then gamma is the summation of these two angles. I should have gamma equal to theta 1 minus theta 2 plus theta 4 minus theta 3, which is 42.8 degrees. Problem solved. Okay? Again, I think for this question, I give you a very important conclusion. That is, okay, the two angles inside the prism, their summation should be always equal to the axis angle. Okay, I hope every one of you try to remember this. This will greatly help you to solve the question in the quiz or the final examination. Yes, before I continue, so let me tell you, so one application for the reflection and refraction, okay? So, you know, the law of reflection and refraction looks very easy, but they are used very often, you know, in a lot of cases, okay? Especially the law of reflection. Let me first talk about the law of reflection. It's always used to get the distance between two remote stars. So for example, if we want to know the distance between Moon and Earth, that is actually, scientists do that by, you know, making use of reflection. So, you know, when astronomers, they travel to the Moon, what they do is they place a certain kind of mirror onto the moon, okay? So, you know, light can travel at a very fast speed. So in order to get, especially the light speed is quite stable in air and vacuum. So how scientists get the distance between our star, Earth, and the Moon is they sending light onto the Moon. Let it reflected by the mirror placed by the astronomer, right? And then they detect the time delay. They send a light to the Moon. If there is no mirror, of course it will be absorbed or scattered. But if there is a mirror, it will reflect back to us. By get the time delay delta t, c times delta t is twice of the distance between Earth and the Moon. And then scientists calculated that is about, you know, 30.84 times 10 to the 5 kilometers. Okay, 10 to the 5 kilometers. Okay, so that's the law of reflection is very helpful, can help us to calculate the distance between a remote star and Earth. Okay, this is very important. So then let me talk. Any question again about question 2? So if not, let's take a look at question 3. Question 3. Okay. So this question asks us to determine the maximum angle theta for which light ray incident on the end of the pipe shown in the figure below will subject to total internal reflection at the wall. Total internal reflection at the wall. Okay, what we know is the refractive index of this fiber, of this optical fiber, is equal to 1.36. 1.36. Okay, so this is the configuration we are looking at. The question wants us to calculate what is the angle theta in order for light to subject to total internal reflection at the wall. So that here at the left interface, okay, may I have your attention please? So at the left interface, okay, if you apply Snell's law, you have 1 times sine theta equal to the refraction index n, which is 1.36 times sine phi. But, you know, as I already told you, in order to apply Snell's law to solve a certain angle, we have to know 3 parameters out of 4 in the Snell's law. But for this question, we have 2 unknown parameters, theta and phi. So just the Snell's law, apply Snell's law once at the left interface, at the end, okay, left end of the interface, will not be enough for us to solve theta and phi. So we have to apply another law, so which is total internal reflection at the wall. Total internal reflection at the wall, okay? So that if you have total internal reflection at the wall, what you can do is directly solve what theta c it is. What theta c it is. Theta c equal to NL divided by N pipe, okay, equal to, which means theta c should equal to 74.3 degrees. This is directly, you know, learned from the total internal reflection. So now if theta c is known by looking at this right angle, you can directly say my phi should equal to 19 minus theta c. Then phi equal to 90 minus, let's say, then we get 42.7 degrees as phi. Then phi is known, we can directly apply Snell's law at the left end, because in this case, N1, N2, and phi are both known. We can get theta equal to 67.2 degrees. 67.2 degrees. Okay, so these are all the 3 steps in order for you to solve this question. But of course, if you learn the summary lecture, you will be able to use an even simpler procedure to solve this question. So that is called the numeric aperture. Okay, so the numeric aperture is defined. Yes, the numeric aperture is defined as square root n2 square minus n1 square. So what's the physical meaning of the numeric aperture? The physical meaning of the numeric aperture is sine theta I. So it's a sine function of the maximum, incident angle for which light subject to total internal reflection at the wall of the fiber. That is the meaning of the numeric aperture. Okay, the numeric aperture is exactly the sine function of the maximum incident angle here. So that light will subject to total internal reflection at the wall. So if you know this, you remember this. What is the meaning of the numeric aperture? That is actually sine theta I. And then in your formula sheet, okay, in your final examination formula sheet, it will directly tell you the NA. That is the numeric aperture equal to n2 square minus n1 square, and then we do another square root. Okay, then you understand this NA is actually equal to sine theta I. You directly equal sine theta I equal to square root n2 square minus n1 square. Okay, you will be able to solve this question, quite fast. Okay, and it's the same as what we do before. Okay. So the second way to solve this question is directly use the definition of numeric aperture. Okay, directly use the definition of numeric aperture. Okay, any question? Any question? Okay. So no question, I will move to the next 4. Okay, question 4 is perhaps the most difficult question. Okay, perhaps the most difficult question of this tutorial. So here we have a narrow beam of white light. So white light consists from, as I said, red, yellow, green, blue. Okay, each color, a lot of color here. So a narrow beam incident at an angle 25 degrees onto a heavy flint glass slab, and the thickness of the glass slab is 5 centimeters. Okay, the thickness of the glass slab is 5 centimeters. The refractive index of the glass at the blue light and the red light, wavelengths is 1.689 and 1.642. Okay, so at the blue and the red are these two refractive index respectively. The question asks us to find out what is the thickness of the light beam that emerging from the transmission side. So first we need to understand what this question means. What this question asks for. So this question tells us that in the past we have a white beam with a 0 thickness. It's just a white laser beam. Okay, the thickness is the width of the laser beam is 0. Once it passes through the interface, because we already know the glass has a chromatic effect, so that it will exhibit different reflective index, for different light color. So red light says the smallest reflective index, violet light says the largest reflective index, so that they will be refracted along different directions inside the glass. Okay, so if they reflected along different directions, the red and the yellow light, they will be separated, right? They will be separated. Once they separated on the transmission from the other side of the glass, they will no longer overlap with each other, but separated with each other by a certain distance. Okay, but separated with each other by a certain distance. Okay, and then which means originally the instant light ray have zero thickness. After passing through the glass slab, now the width of the laser beam, because the red and violet light, each color, they are no longer propagated along the same direction, they will be separated. What the question wants us to do is to calculate the thickness, the width of the two beams. So actually that is the distance between the violet and the red light. Want us to calculate the distance between the white and the yellow light. Because of the achromatic effect, the red and the violet light, they will be separated. So what the question wants is for us to calculate the distance between these two light rays. The distance between these two light rays. Okay, so before I continue, I think this is very important. You have to understand what this question asked for. So any question here? Yes?
Sorry. Yeah, but it's different refractive index, right? So it won't be carried out anymore, the emerging rays.
Oh yes, so you mean that distance will be larger and larger, right?
Yeah.
Yes, this is what I would say. Inside the glass slab, it will be larger and larger. But after passing through the slab, and then they will be still propagated along the same direction. So they are parallel to each other. So that their distance will not become larger and larger. Only for the two parallel rays, you can define the width. Otherwise, if the distance continue changing, there is no way for you to define a distance. This is.
I mean, like when it emerges, it shouldn't be parallel anymore.
Yeah, it will be parallel anymore. This is what we will prove. They very good, yes. This is what I will talk about next. You have to prove these two rays are parallel to each other. Inside they are not, but outside they are actually parallel to each other. When they emerging on the other transmission side, yes, this is a very good question. This is what I'm now going to prove that these two rays are still parallel to each other. So that their distance is fixed. Otherwise, if they are not parallel, their distance is changing another propagation direction. Okay, so very good. Okay, so now let me prove why these two rays are still parallel to each other. So the way I doing this is apply, for example, first for violet light, I apply Snell's law at both interface. Okay, here I assume inside the slab this reflected angle here is theta 2V, and then the final reflected angle here is theta 3V. So apply Snell's law at the first interface. I have 1 times sine theta. Theta 1 is 25 degrees. Okay, equal to NV, the reflective index of the violet light times sine theta 2V. At the second interface, okay, because of these two interfaces are part of each other, so that the incident angle here should be theta 2V, okay? Then my NV times sine theta 2V should equal to log 1 times sine theta 3V. Now, if you look at the combine the first and the second equation, you can directly say my 1 times theta 1 sine theta 1 equal to 1 times sine 3V. No matter what reflective index NV it is, this equation always holds true. So in other words here, my theta 3V should equal to theta 1 equal to 25 degrees. Theta 3V should equal to theta 1 equal to 25 degrees. So you can say I get this conclusion by without using any NV here. No matter what N it is, it will not change the final emerging reflected angle. So if we apply Snell's law for the red light, okay, you can do the same. You just change NV to NR. It will still give you sine theta 1 equal to sine theta 3R, so that my theta 3R should also equal to theta 1 equal to 25 degrees. Because my both theta 3R and this theta 3V are equal to 25 degrees, which means they are still reflected on the transmission side, they are still propagated along the same direction. These are the two parallel rays, so that the distance between them is unchanged. Okay, but inside you can say they are another propagation direction. They propagate on a different direction. The distance become larger, larger, and larger. But after they passing through, transmitted through the slab, the distance no longer changing because the two rays are now parallel to each other again. Okay?
It's only because the two sides are parallel to each other, right?
Yes, very good. If this is a present, if the two sides are not parallel to each other, you do not have this condition. So this is why Newton, okay? Newton, when they passing this white light into a prism, and then at the other side, we get this rainbow, okay? Because this light, different lights still project on different direction. But if we have a slab, the two interfaces parallel to each other, so the color will be separate, but we cannot get a rainbow. After that, the light are still propagate parallel to each other. But if you have a prism, these two interfaces not parallel to each other, and then this rays will no longer parallel to each other. Yes. Okay. Other question? Other questions? Okay. So if no, let's look at how to solve this. Now, what we want is the distance between these two parallel rays. So what we should look at is, this small bit. So first, you can say what we need to know is, the difference in the y coordinate of these 2 points, or we say this is delta y, this is delta y. Then if delta y is low, we look at this right angle. Okay, this blue dash and black, hypotenuse, this right angle. So that if we know this is A, so later I will show this A is actually theta 1. Okay, later I will show this A is actually theta 1. If we know both delta Y and A, and then the weight W here should be calculated as how much? Calculated how much? Delta Y times cosine A, right? Should be calculated as delta Y times cosine A. So in the following, what I will do is calculate delta Y and A respectively. Delta Y and A respectively. First delta Y. Okay, first delta Y. So for delta Y is actually, as I said, is equal to the difference between y coordinate of these 2 points. So we'll first calculate what is the YR and the Y2, these 2 points it is. Okay, so you can say for this YR, this bit is always equal to 5 because the thickness here is 5 centimeters. Is equal to the 5 centimeters times this tangent theta. So for red light is tangent 2R, okay, 2 theta R. So for yellow light, okay, for blue light, of course, it should be equal to y times tangent 2v, okay, the refracted angle for blue light. So that we just apply Snell's law for red light first, okay, n1 times sin theta 1 equal to n2 times sin theta 2 sin theta 2. Substitute the refractive index for red light into the equation. You can get theta 2 is equal to this value. 5 times sin theta 2 give us 1.3318 centimeters. And then we do that for violet light. For violet light, changing this guy to the refractive index of the violet light, so that we will get a smaller refractive index, which gives us a smaller y coordinate, 1.292 centimeters. Then delta y is equal to the difference between the 2 y coordinates, okay? So this is about, okay, 0.0396 centimeters. This is delta y. So knowing delta y, we do W, we need to get what is my A. What is my A? So to get A, you need to look at this right angle on the surface normal. Okay, you can say theta I here is 25 degrees. Theta I plus this angle is equal to 90. Because this is a right angle, A plus this angle also equal to 90. Clearly, my A is exactly 90. Okay, is exactly 90. Is 90 for minus this angle is 90 minus I, so that I have A equal to theta I equal to 25 degrees. So now both delta Y and A is known, so my W equal to delta Y times cosine A, which is 0.359 meters. Okay? Any question? Yes, any question? Any question for student online? Any question? Okay. So if no question, let's look at the last question. Okay. Let's look at the last particular question. Okay. So I think this question is quite easy, right? So only have 2 parts. So this figure here shows the path of light beam passing through 3 parallel slabs, okay, with different refractive index. So the incident angle at the first interface is equal to 30, theta 1 equal to 30 degree. The question wants us to calculate what is the angle theta 2 at the final interface. Then what must be the incident angle theta 1 to be in order for total internal reflection to happen at the last interface? Okay, what should be theta 1 if I want the total internal reflection to happen at the last interface? Or what should be my theta 1 it is if my theta 2 is 90 degree? Total internal reflection is to calculate the maximum incident angle, so that here will be 90 degree. This guy will be 90 degree. So let's look at this question one by one. So now the interface are still, all part of each other again. So that if we assume this angle, the first refractive angle is alpha, and then the second incident angle here, theta, should also be alpha. Now we assume this is beta, and then at this third incident angle should also be beta. And then if you apply Snell's law at this three interface, so at the first interface, I have 1.4, the refractive index times alpha, equal to 1.6 times theta 1. So this is 1.6, 1.4, 1.2. So that 1.6 times sine theta 1 should equal to 1.4 times sine alpha. At the second interface, my 1.4 times sine alpha should equal to 1.2 times sine beta. Last interface, 1.2 times sine beta should equal to sine theta 2. So if you list these three Snell's law together, you will get the three equations like this. So that you can say this side equal to this side, this side equal to this side. If you directly equal to the final 1 point sine theta 2, it should remain unchanged as 1.6 times sine theta 1. So theta 1 is given, refractive index is known here. We can directly get my theta 2 equal to arc sine 1.6 times sine 30 degree. Sine 30 degree is equal to 0.5. So this guy equal to 0.8. Arc sine 0.8 is 53.1 degree. 53.1 degree. So the first part solved. So for second part is ask us what will be the angle theta 1 in order for total internal reflection happen at this interface. So in other words, we should set theta 2 equal to 90 degree. Theta 2 equal to 90 degree. So still looking at this equation, set theta 2 equal to 90 degree, and then you will be able to calculate what my theta 1 it is. As I said, okay, theta 1 should be equal to arc theta 2 divided by 1.6. Total internal reflection is theta 2 equal to 90. So that we get theta 1 equal to 38.7 degrees. 38.7 degrees. Okay, so now I think I still have some time to give you some another one or two examples. Okay, so previously I talked about the law, how the reflection can help us to do some useful things. For example, measure the remote stars. Now I can tell you what can we make use of the law of reflection. The law of reflection can help us to make an object invisible. For example, you can use the law of reflection to build Harry Potter's invisibility cloak. What we do is we properly control the refractive index of the coating, so that the light ray incident upon the coating will be smoothly guided around the object we want to cancel, we want to make invisible, and then smoothly return the light back to the original path as if it just passing through vacuum. Okay, as if it's just passing through vacuum. So in this way, if you can properly design the refractive index, let light ray propagate in this way, something will be invisible from our side. Okay, from our side. Okay, so using this principle, I built an optical cloak about 10 years ago. So this is an experiment I do here. I just properly control the refractive index. So here I have a certain region. Okay, I have a certain tube here. I get light around the tube so that you cannot see. But if you look at this, watch this video. You watch this video here, you can see I hide a golden fish. You can see the tail of the golden fish. Later, the head will go through here because the region here is clear inside. Okay, this is a golden fish. I hide it with my cloak using the law of reflection. Yes, you can see the fish outside, but inside, because of the existence of the cloak, the presence of the cloak, the body of the fish is gone. So as if the light just passes through the vacuum. Okay. So this is what we can do using the invisibility cloak. So then I have another time, maybe 3 minutes for you to. So here I provide another additional 5 past examination papers, but I don't have time to go through one by one. In the past, I have 2 hours. So that I will have another, half an hour to go through maybe another 4 examples. But I only have a time to quickly go through 1 examples. So if you want to know how the solution of the case, you take a look at it yourself. Okay, you take a look at it yourself. But here, what I would like to talk about is this one. That was just tested last year, special term. So here I have light incident upon prism. The apex angle of the prism is 40 degree. So what this question tells us is, okay, at the first and the final angle, the incident angle is 30 degrees. The final emerging angle is also 30 degrees. I want you to calculate the refractive index of the prism. Okay. So if we want to calculate the refractive index of the prism, we need to apply Snell's law. But if we want to apply Snell's law, we need to know what the refracted angle it is, or what we want to know is the refracted angle inside the prism. But clearly, we don't know what the refracted angle inside the prism is. What we know is these 2 angles are equal to each other. What should we do? So the way to do this is you draw a line here. Because this 30 degree equal to each other, if you apply Snell's law, okay, at the first and the second interface, even we cannot calculate we cannot directly get what n and theta 2 it is, because for each equations, okay, there are 2 unknown parameters. But what we can prove is, okay, my theta 3 equal to theta 2. Because of the refractive index of here and here are both n. So if they are the same, theta 2 and theta 3 should be the same. Bear in mind an important conclusion: theta 2 plus theta 3 is the summation of angle inside the prism. It should always equal to the apex angle. Because theta 2 equal to theta 3 and their summation equal to 40 degrees, we can directly say theta 2 and theta 3 are equal to 20 degrees. So if you directly apply, the conclusion that the theta 2 plus theta 3 equal to the apex angle, you can directly get my theta 2 and theta 3 should both equal to 20 degrees. Once theta 2 and theta 3 is given, we apply Snell's law at the interface. You can calculate O equal to n just equal to sine 30 degrees divided by sine 20 equal to 1.46. Okay, 1.46. So of course there is another, I can just show you. If the law of reflection is tested, okay, this is taken very often. The prism was tested very often. Okay, try to take a look at all these examples. So also sometimes we will also take. But here I don't have time to go through all the questions one by one, so that you can take a look yourself. Okay. So with this. I would like to end the class. If you have any question, so I will still remain here to clear your doubts. Otherwise, the class can be dismissed. You can leave. Okay, so let me first stop recording. Yes. Before you leave, I have something to announce. Okay. So some students, you may wondering, so whether I can share the solution of my slides. So what I can tell you officially that is no, because school provided us to share the solution to you by any official way. You are allowed to take pictures, but I cannot send my slides by NTU or send you by email. But what I can do is, I will first share this in our MS Teams group that is treated as an official way. Or if you want, you can copy it from my computer. So that is from your own. I cannot share it in any official way because normally the tutorial will have 1 or 2 titles. If you directly remember that, because in the past, always share the solution until then, and then student just remember the solution. They use the method of the estimation methods, and then they actually appeal. So make that case very troublesome. So that school prevent us to share the solutions in an official way. But if the student want to take picture on the copy himself, that's okay. So this is why I say I cannot share that to them or send you by email, but you can get a copy here or download from our MS Team. So now what I will show you here, so student, you can still see my sharing. What I will show you here is for all course, I will just upload it in the file, in this file. Okay, the recorded lecture is also shared here in the recording. Okay, so later I think the MS team is still processing it, but later it will just be appeared in the recording. Okay, recording here is what you will see. The recorded tutorial. I will share the tutorial slides. I will just share the tutorial slides. Okay, upload it here. Now I will just do it now, so that if you want, you can just you can just download here. Okay, you can just download. Now it is here. After each tutorial, I will upload my solution here for you to take a look. Okay. So if no question, the class can be dismissed. You can all leave. So for students who have a question, I will still remain here to clear your doubts. Okay, Yan, do you have any question? I think you sent something. Hello? Yes.
这个就是刚刚
对，
在那个 slide 上面的时候
你说。
那个 slide 它因为它那个 violet 和那个 red light 这两个 light 它那个。
我们先看到这题啊。对。
因为它那个红线不是它那个 wavelength 不是越大，它的那个 index 越小。
对 ，index 越小，所以它的就那个叫什么 index 越小，所以它就 angle 就越大嘛。
是 wavelength 越大，它的那个 index 就越小。
越小，对 ，wavelength 越大 ，index 越小。
哦，但是因为我看的那个之前那个 lecture summary 上面，就是红线是在上面的，蓝线是在下面的。因为 index
不会，那如果是这样子，它肯定是从里面入射到外面。你的 index 越大。
哦 ，index 越大，它 band 就越大。
不，你听我说，你的 wavelength 越大 ，index 越小，对不对？那你看哈，如果我是从 air insert 到我的这种 material 上面，对不对？那相当于是我就是用这个东西要除以我的 index， 你除一个越小的东西，相当于我的 sin 西塔就越大嘛。
sin 西塔越大就是那个角度越大。
对，我的这角度越大嘛，所以说我的那个 incident 的西塔 r 就比西塔 r 要大嘛，所以我的那个 ray 在下面，这个在上面。就是这算出来的，我的西塔 r 要比西塔 red 是要比西塔 violet 大嘛，对吧？对吧？有没有可以画一下？
我有点没转过来。
我给你画一下，就是说，但是如果你是 light， 必须是从里面出来的，对不对？那你就是那这个 angle 的话，那它应该是等于 n times 我的 sin 西塔，那这样子的话，那就是说是我的n 越大，我的这个 reflected angle 就是在 air 里面的 angle 越大。但是你从 air 打的这个 dispersive material 里面，
对，
你的 wavelength 是越大。比如说，wavelength 是越小，应该说越小的话，你的 n 越大嘛。
对。
那但是你的这个 angle 是等于 n times sin 西塔 1， 这给的 sin 西塔 1， 再除以一个 n2， 对不对？
对，再除以里面这个。
再除以里面这个 n2， 你们的 n 越大的话，那你们的 西塔就越小了。对不对？对吧？
也就是说，那个 index 越大的话，就是那个 n 越大的话，里面那个角度就会越小。
越小，对。但是这是从空气打到我的这种材料里面。n 越大，我里面的角度就越小。但如果我是一个 white beam 从里面这个材料打到外面，我估计你就是把这搞混了。他 lecture notes 也画了这个东西。如果我是从我的里面打到外面，那我是 n times 我的 sin 西塔 1，sin 西塔 1是等于我的外面的 sin 西塔 2。
我看一下那个 lecture， 因为我看的那个昨天不是有那个 lecture 那个讲的吗？
就韩国人讲的对吧？
对，那个韩国老师讲的。他是讲，因为我看的那个 lecture 上面是红的，下面是蓝的。上面是红的，下面是蓝的线。
你估计我觉得你说的应该是另外，你把那个找出来。 你把那个找出来。
找得到，我现在好像他可能还没发上去，可能。
不可能啊 ，lecture notes 已经有了，lecture notes 肯定有了。你是说他昨天的 summary lecture 对吧？
对。
summary lecture 应该在这里面都有的。
就是那个 chromatic 那个东西。
就是 chromatic。
就是这个。
我来找。不应该在这里，你这个都是我也不能找到那个 chromatic。
应该还在下面。
对，说是这个。
你看，这就是那个图。你看这个图，它是红的在上面，蓝的在下面，它是这个样子的。
那这个是因为我们这个你看我们这里是从那个叫什么往下面的嘛。如果你是这样子的话，那它当然就是红的在上面，蓝的在下面了。如果我是从这样子的，
因为它是要对标这个
对，是要对标这个线啊。你是要对标那 surface， 你看的是 surface， 我要对标 surface low 嘛。如果是这样子的话，对不对？我的红线那个 angle 那个大嘛 ，angle 大它更在上面了。但这样子我是 angle 大，我是要对标下面它，那你讲 angle 越大就越下面。但是如果你是从下往上打，那 angle 越大就在上面呀。你是从上往下的话，那 angle 越大就在下面。所以你叫你这个 prism 看它转了180度啊，是的，转180度，那红线就在下面去了。
谢谢老师。
行，没问题啊。好。Any question?
Can I take photo of the question for?
Question for this one.
Division.
Yes.
Yeah, the next slide.
This one.
Which slide is it before this?
Sir.
These two.
This two, yes.
Yes.